So, good morning, everyone. It seems it's 8:30, so we will start. First of all, I want to thank the organizers in the European Space Agency to invite me here to give this presentation, this lecture, and later on the exercises. I hope there is something for all of you. I'm pretty sure some of you will have heard things that I will tell you in the following, because I will also give a little bit of background on glaciers. But as I have seen from the participants list, not all of you are working with glaciers. So I hope it will not be too boring stuff in this case. So yeah, my name is Frank Paul. I'm from the University of Zurich in Switzerland, and the title of my presentation will be Glacier Mapping with Multispectral Satellite Data. And that's a little bit a mixture of, yeah, let's say, introduction to the exercises that you are expected to do, and yeah, some more general background, and of course, the method, how do things work. To give you an overview, I will start with some words on glaciers and climate, so to give the background on why do we map glacier extents, so why this is important. Then you have heard yesterday already quite a lot about it, the spectral properties of glaciers, snow and ice, and the satellite sensors we use to get them, glacier mapping itself, so the algorithm, and then the result of it, so the product, glacier inventories. I will also tell you a little bit about uncertainties, some highlights here and there, and then there will be a summary. In the end, there is certainly some time for questions, and I will also add some practical notes, but not too much. Okay, let's start with glaciers and climate. As you might know, we have 275,000 glaciers on this planet, roughly, and let's say according to the latest global inventory that we have. And we go here from a minimum size of about 0.01 square kilometer, which is the size that has been, let's say, about agreed in the community as things that might still move, which would be required for a glacier. And a maximum size of about 8,000 square kilometers, which would be the Flade East Blink in the northeast of Greenland. And of course, glaciers can be found in all regions in the world, from polar, Arctic and Antarctic regions where it is cold and enough snowfall, and also in tropical regions, then of course only in the higher mountains. And depending on the climatic conditions in the regions where these glaciers are, and of course also the topographic conditions, glaciers have very different shapes. And you see here a selection of a few. If this mouse works, there are those that are very nice to map, like here on Ellesmere Island in the lower right, where you don't have debris cover on top and see the glaciers very well. But then we are also here in New Zealand on Tasman Glacier in the lower left, where the glacier is completely debris covered and actually hard to distinguish. And of course, there are all kinds of interactions with water. So glaciers can have their fronts calving into lakes or the oceans, and or just do dry calving so that you have maybe a regenerated glacier a little bit at lower elevations. And then you have to ask yourself, when you do single part polygons in your inventory, if this lower part should be a part of the upper part, so to connect the two or not. So it can get quite complicated. However, we want to map all these precisely as good as the satellite data allow. And this means that we are fully, we fully rely on spectral properties and our imagination, let's say, about how a glacier flowing from high elevations to low elevations might look like, and where its shape tells you where it is and where it is not. So also from a remote sensing perspective, the main components you will see from the satellite is, of course, here shown for a small valley glacier in Switzerland, which you also have to map. This is the Oberaar Glacier. The region with the snow in the higher elevations, the bare ice in the lower elevations, then here bare rock, and some debris cover. And the upper part and the lower part is usually with some good contrast between the snow-covered region and the bare ice, so that you can distinguish the accumulation and the ablation region. And of course, there's glacier flow, causing also crevasses and transporting the snow from higher elevations to lower elevations. The critical part, and you will see this when you map glaciers, because this glacier mapping does only map the snow and the ice, but not the debris-covered ice. The critical part is then, and maybe we come to this point in the exercises, to tell which part of this debris-covered zone here is on a glacier and where below is already bare rock. And I can show you here how this glacier looks from the satellite perspective. And you see here maybe on the right-hand side of the glacier that here the dark, partly debris-covered parts can be mapped quite well. But here in this region, you will certainly have some struggles, and this is the core of why it takes so long to create a glacier inventory from satellite data, because we want to include this part. As mentioned, there's glacier flow, and this flow takes the mass from higher regions down to lower regions where the ice melts. And you see here in this animation over a summer period for Trift Glacier. It was in 2005, so in the meantime this glacier does not exist anymore at this place, that despite the mass flux here from the steep part coming down into this region, the glacier melts down, also retreats a little bit, and here you can nicely see directly how the ice is converted into water, filling lakes and contributing to sea level rise. And this retreat of the glacier tongue is, of course, very specific for the glacier. So you might have seen these curves before, showing the cumulative length changes of the termini. And the different curves are for different types of glaciers. So you have the large ones, which have very long response times, like Rosse-Aletsch or Pasterze, shown here in black and purple. They provide you the centennial climate signal, so just the temperature increase in this case and the response of the glaciers to this as major forcing. But then you see also some of these wavy curves, so smaller glaciers, often with high elevation, large accumulation regions and short tongues, which react more on a decadal time scale and are very sensitive to fluctuations in precipitation. So when there is maybe a little bit of cooling, but not too much, and more precipitation than usual, for the Alps, for example, depending on the phase of the North Atlantic Oscillation, these glaciers might advance, and they do it all more or less at the same time. So here for Hornkies in the Zillertaler Alps, Lys Glacier, and Glacier du Trian, you see that around the 1960s to 70s, these glaciers start to advance with a peak around 1985. and that there were also in the 1920s and around 1890 these advanced phases. And very small glaciers like Pitzol, they do just fluctuate a little bit, but have still the overall decreasing trend of the length. So when you are asked why are glaciers these compelling natural climate indicators, the point is very simple to make. So when you look here at the purple curve for Pasterze, you see about a retreat of 1,250 meters in, let's say, 125 years, which gives you a retreat of 10 meters per year or 100 meters in a decade. At the same time, the temperature has increased by about, let's say, 1.25 degrees over these 125 years, which gives you a temperature increase of 0.1 degree over 10 years, or 0.01 degree per year. And it is maybe no wonder that there might be some, let's call them climate skeptics, you know what I mean, might not trust this kind of information. Can we, or are we able to measure this as precise so that we can really say it's 0.1 degree temperature increase over 10 years without changing anything in the surrounding of the meteorological stations? Of course we can, because we have not only one station but 10,000, so this works quite well. But a 10-meter change per year or a 100-meter change in the length as a response to the climate change is something that is much more reliable and convincingly to tell as a consequence of climate change than this 0.1 degree. So this makes the glaciers the best natural climate indicators, at least the changes. And to give you a little bit of illustration, you have seen these pictures likely before. I have copy-pasted this from the internet, and I have to give the source on the slides before I send them for making them available to you. This is a picture from 2009, and 9 years later it looks like this. So these are roughly aligned just by some fixed spots that you might see. The rest is not perfectly aligned, but you see how things happen. And of course, there's quite some fun when you can go down to the glacier and then go on the glacier. And you might see here these dots, which are all tourists enjoying the ice. But now you have to go kilometers through wasteland and might not even go on the glacier because it's too dangerous due to all the other things. So this is just the change we have experienced, and things are going fast. Then you might know there are also webcams. And of course, one of the very nice webcams from photowebcam.eu has been on Pasterze Glacier since 2015. And when you take at the same time of the day, around 11 o'clock or 11:10, a picture with good blue clear skies, end of August or September, put them together in an animation, you see, I think, quite well what it means in regard to down wasting. So these low-lying tongues really suffer from the strong heat and just go down, which is, of course, again, a consequence as through this small zone of mass flux into the lower part, this is just not sufficient to sustain this lower part of the tongue. So you can be pretty sure that in your lifetime you will experience that there is no Pasterze Glacier in the valley at all. There might be a lake, it might be a lake full of sediments and not so much lake, depending a little bit, but this lower part of the glacier will disappear. So you can witness this by a webcam and see how things work. When we change now to the satellite perspective, I have here a picture from two mass balance glaciers, Grise Glacier to the left and Basodino to the right. And this image has been taken by Landsat in the hot summer of 2003, which some of you might maybe remember. It was very hot. And at that time, glaciers had still, let's say, a little bit of snow and firn left. Of course, the darker parts you see here, this is all firn, so ablation region. The only snow left might be really these white spots, and maybe also here. So there is not much accumulation at all. The glaciers are more or less with complete negative mass balance. Still, there is some firn that might be converted to glacier ice at some point. However, in 2022, things look like this. So I go a little bit back and forth so that you can follow on both images how the glaciers disappear, like this one up here, which is now more or less melted away, and that also the firn reserves have been destroyed. And now, you might remember yesterday's lecture from Helmut Roth, where it is all about albedo and the change in spectral reflectance. When you now look closely, in this case, you might still say the lower parts of the glaciers, where the ablation region and the dark polluted ice is darker than the higher parts, where the snow and the firn is. And when you look here, now it's vice versa. So now the higher parts, so the previous accumulation regions, are more dark, dirty, as the ice below. So you can likely imagine what this means for the mass balance of a glacier when it is darker at the higher parts, where the accumulation should take place, and brighter in the lower parts. Of course, this bright is still not bright. We talk about reflectance values close to 0.2. But now we have the 0.1 in the upper parts. And maybe you might see a satellite image from 2023 at some point. There we had also very negative mass balances in the Alps. And there is some bright snow left in the highest parts. And you have the very crazy looking impression of a white band, then a dark band, black as coal, and then the blue ice below. So it looks really strange, and of course, when you do not consider this in models, mass balance models, and no mass balance model working on a larger regional scale does this at the moment, it will not work because this is not what we see. So glaciers are darker now in the upper parts than in the lower parts. Glacier retreat is not only a point in the Alps, it's globally. And I just show you here an example from Patagonia, which is a 15 years animation. And you see here 3 larger glaciers that retreat. And please consider the scale here. So luckily not all glaciers, but for example, this one here has a retreat of about 2 kilometers in 15 years. This is the range of alpine glaciers in 150 years. So the retreat in Patagonia, in this part of Patagonia, of the large glaciers, despite the maritime climate with lots of snow, is much, much faster than in the Alps. So it's really like crazy, and you can download the pictures from the servers and put them together and do such animations all around the world. It does not look everywhere this strong, but you see basically, maybe apart from the Karakoram, you see all around the world this trend. What's of course also interesting, but I will not go into detail here, these smaller glaciers a little bit higher up they do not change at all. They show a little bit of shaking, but they still have snow, and there is very little retreat. So it's just these three larger tongues being at low elevations that suffer really from the heat. So this is maybe already some good motivation to map glaciers, but the two basic questions we want to answer when doing this is we want to know how much glacier ice is out there and how fast do glaciers change. One is the glacier distribution. For this purpose, we create glacier inventories to know where they are. And then we have the glacier change. And the glacier inventories, these are done these days from remote sensing data. So this is the exercise of today. You see here some sentinel tiles are 100 kilometer in dimension, and in blue the glaciers in the Alps, which is the base information of where the glaciers are and where the perimeter is. Once we have this, we can use it as an input for models that look at ice thickness distribution, for example, to get the glacier volume. So these are the two things we want to know as a starting point. Where is the ice, how large it is, and how thick the ice is to have the volume. What is absolutely, completely irrelevant, but always asked, how many glaciers we have. It depends on how you count them, how you divide them, where you put the drainage divides, what your minimum size is, and so on and so on. So the size of the glaciers or the number of glaciers and the change in the number of glaciers has absolutely no glaciological meaning, because when glaciers fall apart into several pieces, you have an increase in the number. Yeah, which is maybe not what people want to hear. So forget about the number of glaciers. It's the size and the volume that matters. How fast do glaciers change then is an issue of field observations and also remote sensing. So here for the length changes and the mass balance, two examples for the field observations that are still done on a considerable number of glaciers. So let's say about 1,000 globally for the length changes and a few hundred, depending on the year, for the mass balance. And then we have the remote sensing part, where we go to different techniques. A few have been mentioned already. This is differencing of digital elevation models, altimetry from laser or radar, and gravimetry for the larger ice masses. If you want to know more about these techniques, please have a look at this publication from Etienne Berthier, published in 2023. You will find a link on his homepage. There is a review of all these methods and what they show and how they work. So here just a few points of why now glacier outlines are important. I've already mentioned it. They're needed for all, really for all, glacier-specific calculations. So from mass balance and velocity fields to snow cover and albedo and whatever. They're also a base, of course, for change assessment. You need a baseline data set to determine the changes. Modeling of ice thickness as shown, runoff, future glacier evolution, and so on. These all need glacier outlines as an input. And they also serve as a mask when doing co-registration of digital elevation models, because you need stable terrain outside of glaciers. The same also for velocity. There you also determine uncertainty of glaciers, so to say, so you must know where do you have no glaciers. And they tell us about climatic conditions, so temperature and precipitations at the location where they are. So this already includes this. And their changes tell us then about climate changes. So for example, the retreat or the change in the equilibrium line altitude. And the data set that has been created for the community was for a long time the so-called Randolph Glacier Inventory, or RGI version 6, which has been published, I think, in 2017. And since 2023, so last year, we have the latest version of this global inventory, which is now much more precise in many, many regions. So there's a large community behind it, getting the data better and better in time. However, it still refers to a snapshot around the year 2000 and is not multi-temporal, which is the case for the GLIMS Glacier database, Global Land Ice Measurements from Space. There we have all data sets that have been created included. So if you want to see how glaciers have changed through time, you have to go to the GLIMS database. And the creation of this Randolph Glacier Inventory is coordinated by a working group of the International Association for Cryospheric Sciences. And of course, this group works basically without funding, as it is very hard to obtain funding from scientific, mapping for the purpose of just mapping, because this is no science. So this is then the main reason why it takes so long. These glacier extents, we have them freely available in the database. It's just done step by step and not in a large coordinated effort with lots of money to do it. As a rough estimate, and I did this 20 years ago and it still holds, you can say that once you have mapped the glaciers automatically and then have to do the work for the individual glaciers and check the debris-covered parts, you need about 10 minutes for one glacier. So you can multiply this 10 minutes with 275,000, and then you know roughly how much time would be required to do one global glacier inventory. So these glaciers cover 705,000 square kilometers. For comparison, I think the Greenland ice sheet has something like 1.6 million square kilometers. So it's a little bit less than half of it. And they combine a volume of 160,000 cubic kilometers, which is about 30 centimeters of sea level equivalent. And you see here on this picture what is new in the Randolph Glacier Inventory 7. So all these red regions have been reworked and were partly have lots of improvements, and the blue ones are still those from the former RGI 6. And putting it together, here is the book, or the one publication describing the Randolph Glacier Inventory. And this is the rest of modern research in mountain glaciology. So they all need the data, and you can make your nice science nature publications not without it. So, which means that the paper from Ted Pfeffer describing this first version, I think 3.2 of the Randolph Glacier Inventory, is now the most cited in the Journal of Glaciology, because it's just the baseline data set for lots of work that is currently done. So, spectral properties. That was, so to say, the background blah blah, and I should now come to some more essential things. And the good thing is we already heard or had some good introduction yesterday in some of the aspects, so I can go maybe quickly through it. With the optical sensors, we look at visible light, meaning blue, green, and red, which you can also see with the eyes, and where the optical sensors have also their bands. And then we have the near infrared, something around 0.7 to maybe 0.9 or 1 micron. And then we have the shortwave infrared, which is then from 1 micron to, let's say, 3. And all the rest, the radar, you have seen yesterday. I will not go back into this. So we focus now on this range to the left. And you have seen this slide also yesterday, or at least a part of it. This just shows the atmospheric transmission as the curve you see in the background. And the point here is that all optical sensors, be it ASTA or Landsat or Sentinel or whatever, they have their bands about at the same place. So the method to map glaciers is largely exchangeable because the so-called atmospheric windows, or where the atmospheric transmission is sufficiently high, allows to see the Earth's surface. And so all designers of sensors have to adhere to this. But of course, there is then some mixture of the numbers, so they change a little bit. I'll show you this in a second. And maybe here, I think this has also been shown yesterday, we identify things by these spectral bands, as in the different spectral bands, the spectral reflectance of different materials might be different. For example, green vegetation has very high reflectance in the near-infrared due to the chlorophyll, which means that in natural colors you might not be able to distinguish or say if this grass here is natural or this one here, but in the near-infrared you can tell it immediately because with a very high spectral reflection here, when you use a near-infrared band and a red band and a green band as an RGB, red, green and blue composite, you can easily distinguish the two, at least as long as the vegetation is healthy. So when the vegetation is not healthy, then also the red goes more to gray, and this can then be used, of course, to map trees which are not healthy. Same for snow and clouds. They have very high reflectance, at least in the visible part of the spectrum, but the cool thing is they don't have in the shortwave infrared. So in the shortwave infrared, and you have seen this curve also yesterday for snow of different grain sizes, the shortwave infrared, so here between, let's say, 1.5 and 2.5 micron, the reflectance of snow is very, very low, and of clouds is still quite high, so that you can spectrally discriminate these different pieces. And this has been shown also yesterday. There is a dependence on grain size of the reflection. The smaller, the finer the grain size, the higher the reflectance. And if you now imagine that glaciers are composed of snow with very large grain size, so to say, it is clear that glacier ice is here at the lower part of the curve, which means around 1.5 micron, and glacier ice has a reflectance of about 0. So when you walk over a glacier and your eyes are sensitive to the visible light, as they should be, you should wear sunglasses. But if your eyes would be sensitive to the shortwave infrared and only to this part, you really need some light amplifier to see something, because it's much darker than coal. And of course, we can use this strong difference in spectral reflectance to map the glacier ice and snow. You have here the table where the band numbers of the blue, green, red, near-infrared, shortwave infrared, and panchromatic bands of the different sensors. This is just for your information. I have this also then later on in the my material for the exercises, but as far as I know, you will also get these slides, so you can look it up. And there's also a publication where I have created this table. The colors indicate the different spatial resolutions. So black here means 30 meters, and gray is 10 meters, red is 20 meters, and blue is 15 meters. And as also said yesterday, when the ice is polluted, of course you see the spectral curve of the material on the ice and not anymore of the glacier ice. So when you do the bend ratio mapping, which I introduce in a second, you have to go through these different channel combinations. And this overview just shows how glaciers might look in the different spectral bands. Here is again Oberaar Glacier with a lake in front of it. And you see there's not much change in these blue, green, and red bands, so they look about similar. Near infrared then, you see here this strong contrast where there is a little bit of forest that is very bright here due to the chlorophyll reflection and very dark in these other bands. And you also see that the contrast between ice and snow is strongly improving. So here we have still some kind of saturation over snow, and here in the near infrared it is much clearer. Shortwave infrared now, this is the part where the glaciers are dark. The surrounding terrain is very bright in the shortwave infrared, at least compared to the other bands. And you might see here in this region, it is a little bit of not as black, so dark gray. And this is the effect due to the different grain sizes. So you have in the highest parts of the accumulation region, there's little metamorphosis of the snow, so the grain sizes are still very small, which means that in this region also the reflectance is a little bit higher than further down where the grain sizes or the glacier ice is very large. And this thermal band is not available from Sentinel-2, as we have heard yesterday, but you see the temperature, which means when it is cold, here indicated with dark colors, and if it is warmer, then it has brighter values. So this sunlit, south-exposed terrain is very bright, compared to the north-facing slope, which has no sunlight at this time of the day. And of course, the glaciers are dark, but where they are debris covered, like here for Unteraar, of course, the rocks heat up a little bit, and so they are similarly bright. And when you now combine these bands as red, green, and blue, you get this natural color image, which is not very colorful, because the bands are spectrally very similar. But when you do it now with the near infrared as red and the green, the red as band as a green band and the band 2 as a blue band, you get these false color composites, which show vegetation in bright red colors. And lakes and water in this bluish tint. So this is here lake. When I now ask you for this picture, where is the cloud? Would someone be able to tell me? Maybe not, because the contrast is really bad, but maybe some of you have good imagination. Does anyone? It's a small cloud, so not very large, but it's a cloud on top of a glacier. But I think I can, yeah?
Maybe
In
in the middle of the picture.
the middle of the picture? This is actually, this is a cloud shadow. The cloud is here. So this is why we use this band combination. Here the cloud is not really white, but still you can see it as a brighter, lighter spot. Which means when we correct glaciers, it's always a good idea to have this false color composite in the background to be sure that the, let's say, rock outcrop is indeed a rock outcrop and not a cloud. This back check is quite important. Then just to the spatial resolution, this is the Landsat 30 meter, where generations of glacier mapping analysts have worked with. And when you zoom in to this high degree, you basically see pixels. And of course, some imagination is required to get through. And with the Sentinel-2, now we have 10-meter resolution. And you see crevasses, which means we can identify glaciers as glaciers and not as a collection of pixels. So this change in spatial resolution has really made the job much more straightforward. This is in the background Landsat path row scene. This is for comparison Sentinel-2 path, 290 kilometers wide. Landsat is about 185. And this region here is this region here. So this is the 100 kilometer Sentinel tile. And you need 15 Sentinel-2 tiles to cover the entire Alps. So just as a rough order of magnitude. And I will now focus on this yellow region, where I show you how the glacier mapping works. And I can do this very quickly because you have now seen the basics. So, Aletsch region in natural colors, very beautiful, with a little bit of snow still left in August 2015. This is in red band, so not much change. This is shortwave infrared, so you see this change in spectral reflectance. And the core of the mapping is now we divide the two bands, the raw digital numbers of the two bands, and we get a ratio image. So in this case, a band 4/11. And now we have a very strongly improved contrast of between ice and snow and the rest. And we then just apply a threshold and have our glacier map. So this part of the game takes maybe 10 minutes for a full scene with hundreds of glaciers. But as you see, the glaciers are not complete. So the debris-covered parts are not included, which I can show you here as an overlay. So when you do the raster vector conversion, you get these polygons in yellow, and you see the gaps due to medial moraines or the moraines in the lower parts, and these have to be manually edited. There is nothing from AI to DL and ML and whatever you can imagine that has solved this problem. So it might be at some point, but we are not yet there. So still, this is a work that needs to be done, and this is what takes the time. And here is just that you can then calculate for the polygons the size in square kilometers and then go into the attribute table in the geographic information system and remove everything that's smaller than 0.01 square kilometers. So in the end, you have a glacier inventory that you can combine with the DEM, fill with all kinds of attributable information. For example, you can calculate per glacier then or per zone statistics from different data sets providing the values, for example, a DEM. That will you then give minimum elevation, maximum elevation, mean, median, and so on. Or when you calculate a slope grid out of the DEM, you have the mean slope, mean aspect, whatever you like. And this is, for example, median elevation, color-coded for the value. And when you do then a conversion to a point file and apply this median elevation and do this for a larger region, you can, for example, say something about the precipitation in the region. So here we have the low elevation region with the bluish values, which receive lots of precipitation, and the more green and red ones, which receive very little precipitation. So with some further data sets, you can actually convert the mean elevation of a glacier or median, it does not matter too much, into the precipitation amounts in this region. So this is where a glacier inventory alone gives you already information about a property that is very difficult to obtain otherwise. And you might know Hans Oerlemans, who has used this some 20 years ago to derive out of the glacier changes the temperature curve. Then, of course, you can combine the different attributes. For example, show plots where you have the mean elevation versus the aspect, showing here, for example, that south exposed glaciers are in the mean 300 meter higher in elevation than those to the north. But of course, there is large scatter due to the precipitation change, and you can put things on top of each other when doing it for 2 points in time to do the change assessment. Uncertainties. You will have little with your threshold values. You see here 2 different ones to the left, where the yellow pixels are removed when you decrease the threshold value from 1.4 in this case to 1.38. So it has an impact, in particular in the regions in shadow. These are the most sensitive, and these are the regions where you should look for finding the best threshold, which is the most important part of your exercise today. The problematic point is that when you use Sentinel-2 and not Landsat, you have to do an additional threshold in the blue band, because with this simple band ratio, you get also all regions in shadow without ice included in the map. And these are a little bit darker in the blue band than those regions with ice and snow and shadow. So you have to apply an additional threshold in the blue band to remove these otherwise mapped parts. Okay, but for clean ice, there's not too much difference between the different sensors, and apart maybe from a small shift. And I skipped this. This is just a quantitative assessment. And the very interesting thing, I think we will not do this here, but when you do the delineation by yourself independently a few times and then put the lines on top, or do the same exercise with different persons, then you get quite a spread in the interpretation. And my way then of calculating uncertainty is to use the standard deviation of these different glacier sizes that result from this outline mapping from the mean value of all digitizations. So this is one way to determine uncertainty, and also, of course, to visualize the critical parts. And yeah, there is, of course, a dependence on glacier size. So the smaller the glacier, here smaller than 1 square kilometer, the larger is the difference. But in general, let's say for glaciers larger than 1 square kilometer, we are usually in the range of smaller than 5% with the uncertainties. So relative glacier area difference. Interpretation difference is also a thing when you compare here, for example, the inventory from 2003 with the one from 2016 in yellow. You see that there's lots more ice in 2016 than in 2003. And the main reason here is that there was perennial ice and snow fields still remaining in 2016, but not in 2003. So as these regions have also been mapped, and in part some regions have also been better visible, for example, this glacier up here or this glacier up here has not been detected in the Landsat images from 2003. And so a one-to-one comparison of glacier changes could be challenged by interpretation differences, image conditions, and the spatial resolution that you use. And of course, you have some glaciers. This is here a high-resolution image where you just have to guess where the terminus in this case might be, or which parts belong to the glacier and which not. So these high-resolution images, you can also put them in the background from the S3 base map. In some regions, they are very good, and they help in the interpretation, but not always. And a point that we will not discuss here, but that is, has to be done to get the individual glaciers, is to have a digital elevation model with, applied to watershed analysis to get the drainage divides. So when you have a big ice cap, for example, with individual glaciers, you want to know which region belongs to the individual glacier. And you see here in black the divides from the RGI-6, and in white the now improved divides from RGI-7. And yeah, in particular, this region here shows you some interesting interpretation of drainage divides. which have now been improved. And of course, this also changes glacier sizes dramatically. So you cannot one-to-one compare them through the different inventories. So I'm at the end, that's good. In summary, everyone needs glacier outlines, but only a few create them. Clean ice can be mapped automatically with a bend ratio, but manual editing of debris cover is required and very time consuming. We have only one Randolph Glacier inventory, global inventory, from around the year 2000. And the quality and update frequency of global digital elevation models, I have not discussed this too much, is currently insufficient. So we have much better and much more satellite data and only a few DMs that can really be used to get them geometrically correct in mountain terrain. And if you ever have to map glaciers yourself and think, oh, this is a cool data set, please send it to the GLIMS database, so that is available also for future generations of scientists and can be used there. And the exercise should help you a little bit to find out how this works. With this, I thank you for attention, and I think we have a little bit of time for questions. Are there any questions? I changed my glasses because I don't see anything. Yeah, please.
So Sentinel-2 images come generally in two product levels. So there's level 1C, level 2A, top of atmosphere, reflectance, and bottom of atmosphere. So they, from my experience, they have strengths and weaknesses. So there's a correction factor, for example, for north-facing slopes. This sometimes overexposes or washes out north-facing slopes in high altitudes. Would you prefer either one, level 1C or 2A?
Never use the 2A.
Yeah.
Please only use the 1C in case of Sentinel. For visual analysis and just checking back things, the 2A is fine. But as said before, these shadow regions are corrected with a digital elevation model that does not fit to the data by time and glacier surface height and blah, blah, blah. So it just has artifacts, and it does not work so well. So we don't need the artifacts, because when we do the bend ratio, they would be strongly enhanced. And so please, only for Sentinel-2, use level 1C data. Further questions? Yeah?
Yeah, thank you. Before you characterize glaciers, you mentioned that the median elevation. So how you calculate the median elevations is the median numbers of all the pixels within the basin?
Within the glacier outline.
Within the glacier outline.
Yeah, so
A certain, yeah.
yes, the idea is you have individual polygons for the individual glaciers, and let's say when you do it on a raster base, you convert this data set to a zone. So all pixels of one glacier have the same number, and all glaciers within a scene have a different one. And then you take a digital elevation model as providing the values, and use these zones of the glaciers for the region where the statistics have to be calculated. And then it's just the zone statistics that you can use, and it provides you mean, median, maximum, minimum, whatever you would like to have, standard deviation, and from the underlying value data set. And this could be a DM, this could be a slope derived from a DM, this could be mean potential solar radiation during summer, whatever you have. And you can calculate this per glacier, and then of course, so once you have glacier outlines and the DM, you can be busy for a decade or two. So this is an endless thing. Yeah?
How good is the drainage divide around the Randolph Glacier inventory? And is it done at the same way all over the world? There are some regions that have a better positive drainage divide. Stuff like that.
In principle, yes. So there are regions where we have strongly improved divides, because, for example, for there's an island where I showed the example from. We have now the Arctic DEM with, I don't know, something like 5 meter spatial resolution that was really good in quality, also for these very flat things. And there are other regions where the data set has not been corrected, or only corrected in regard to the drainage divides, but not to the outlines. And it is highly variable. You might download for one region the RGI6 and then the RGI7, where it has been improved, and then just see what the changes are. That there's constant further improvement, I would say, but when you want to be sure, please do not use anymore the RGI6, because there were really strong changes. And RGI7 is much better in basically all regions. But the principal calculation is done with a tool from the OGGM model, and done consistently for all glaciers where this information has not been provided by the data providers. So it is not reworked as far as I know, but done consistently with the same method as for the regions where this info has not been provided. Further questions? Yeah?
In terms of satellite data that is available now, would you say it's sufficient to do proper inventories, or do you have like a wish list for future missions what they should provide to improve the process for the inventories?
I think I've only this one wish list, and that is that we urgently need a new stereo sensor optical thing. I think when there's a continuation of Landsat and Sentinels with free access, we can work along these lines. Higher spatial resolution might be cool, and will provide even better quality, but the main problem is the DEM. So that you cannot create time series when different DMs have been used, or wrong DMs, things do just not match in high mountain topography. It's a little bit different for flat ice caps, of course, that doesn't matter too much, but as long as in steep mountain terrain, things will just go back and forth in the different scenes, and so that would be the main bottleneck, not the optical data itself, but the missing stereo. Yeah.
It helps more spectral resolution for like hyperspectral emissions like NMAP or SHINE, which it helps more spectral resolution in short infrared detectors.
No. You will end up in folding back the hyperspectral things back to the main bands. So you have no gain here, neither in shadow regions nor for the debris discrimination. There it's already now done with all kinds of additional information like elevation changes, flow velocity, ZAR coherence images, blah, 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 to get things done. But spectral bands alone would not improve the situation for the glacier outlines. It would be cool for the snow cover on glaciers, so when you're interested in this, then there could be a little bit of gain, because towards the near infrared 1 micron, the spectral separation is much larger, or largest, as we have seen yesterday, to have different snow grain sizes and discriminate the facies and the film and blah, blah, blah. But otherwise, just for the mapping, no. Good. Yeah?
Thank you for your presentation. I think you did a good job in outlines and boundaries of the glaciers, how to estimate the depth of the glacier. In my opinion, both boundaries and the depths are necessary for the mapping glacier inventory.
Yeah, the ice thickness distribution or depth, of course, this is then done by models, which have some disparity in results. You need the outlines as an input and a digital elevation model, and depending on the model approach, also additional data. So there are a few which use mass flux or mass conservation to get things done, where you have to estimate mass balance terms of all the glaciers, and have, of course, then also related uncertainties. So at this point, the Randolph Glacier inventory with the outlines and also the center lines for the length is one part of the pack, and the ice thickness data sets is differently stored, also freely available, that differently stored. I think there's not yet any consensus data sets. You can use the one from Romain Milan or from Dani Farinotti and colleagues. But of course, with the new outlines and the better DMs, it might be recalculated and we get a new one. And maybe at some point, both are also stored in the same region so that users can use both at the same time for a full characterization of the glaciers. I just want to add, because we are now done, I will show this likely also in the room where we have the exercises, where these three glaciers where you should the manual corrections are located. So this is likely the only information I have missed to provide. There's this Oberaar Glacier, and then these two connected Bechy and Minstiger glaciers, and then Gries Glacier, where you should do in the exercises, when you come to this point, the manual correction editing of the glacier outline to get the glaciers complete. And for the exercise itself, there is a sheet of paper, a few pages with detailed instructions of how you should do it. I think not all of you have used ArcGIS from Esri, but many of you have used QGIS before. Apart from where the buttons are and how the names of the functions are, there is not too much difference. But we might try to put those who have never worked with the GIS close to persons who have good experience with this. So maybe this works out. But now I stop because we have a further presentation. And I will be here until Wednesday night. So if you have any questions at one point or during the exercises, just let me know. So.
Okay. Okay, so we plow straight on. It must be a bit tough for you. There's no breaks whatsoever, just we plow straight on. But there's a coffee break after this one, so you can look forward to that. So my name's John Merryman. I'll be talking about glacier motion. And I'll be very biased in my talk because I work with satellite radar images, and although you can measure glacier motion both with radar images and with optical ones, I will talk basically only about the use of radar for this purpose. But there's also a scientific reason for this. It is radar images are definitely the primary data source used to map motion. So, for example, it's used to routinely map motion of glaciers and ice sheets in the polar regions. Although optical images can also be used and are also used for the same purpose. We are talking about a different spectral band compared to the ones which Frank has been discussing. So we will, these satellite radars work in the microwave region, centimetric wavelengths. Can you guess any reason why a microwave sensor, a microwave radar, might be more used than an optical sensor for measuring glacier motion? Does any reason come to your mind? Clouds, of course. So microwave radars, as you saw yesterday with Helmut Roth, they see through the clouds, so to say, and that is one region. There are also some more subtle reasons, which we will cover a bit in our discussion. There was a, so this is the, so you will see some things here now in theory. We are going to talk about two measurement techniques, SAR interferometry and offset tracking. Then there was a slight misunderstanding here in the sense that I thought that we had 4 hours exercise together, 2 hours on interferometry and 2 on offset tracking. Instead, we must instead do 2 hours on SAR and offset tracking and then repeat the same exercise for another half of you in the second term. So we will make this work. So actually you will have SAR interferometry compressed into, so you will have exercises 1 and 2 in the material you have for 2 hours in the morning, and then we will repeat that. So I think we will manage. Before we dive into these measurement techniques, I'm going to measure some, and I'm going to mention some general properties of spaceborne radar images which we can exploit for motion measurements, and we will exploit in these two techniques. One, of course, is the image amplitude. So if we look at this microwave picture of a system of glaciers in the northwestern Greenland, the Upernavik Istrum, this is an image from a C-band sensor, so 5.5 centimeter wavelength, MVSat ASAR, European Space Agency sensor, from July 15th, 2010. And now if you focus here on this, let's say on this glacier tongue, I show you an image 35 days later. I go back and forth a bit. So 15th of July, 19th of August. Can you see, if you focus on this central section, can you see anything moving from here to here? Can any of you see anything moving? No? Well, yes? Which way is it moving? Is it moving here to the... That way or this way? This way. Okay, so indeed, luckily, the glacier should be moving towards the ocean, as Frank showed you. And, well, if you see, for example, for me, if I should try and figure this out, my eyes basically lock on some feature, which might be some crevasses or some of the things Frank showed you in optical images. And basically, your eyes will sort of track them going downstream. And indeed, our brain is carrying out so-called feature tracking. We are locking on a feature and trying to follow it by recognizing a moving pattern. Indeed, this is what a computer can also do for us and will do much better than us. And it is the basis for this offset tracking method we will be talking about. However, synthetic aperture radar, the kind of radars which are installed on remote sensing satellites, they are also coherent instrument. They keep track of phase, so there will be a stable oscillator which keeps track of the phase of the pulses which are transmitted, so that when the pulses are received, the transmitted and the received phase can be compared to each other. And why this? Well, the phase is, in a simplified, under some simplifying assumptions, proportional to the two-way propagation delay of this pulse. So the delay from the satellite to a point on ground, and then to also including the time it takes to bounce back to the radar. And this delay is, under many simplifications, proportional to the distance, the so-called slant range between the satellite and the point on ground. So if we can measure the phase, we have something proportional to the distance. So we have some position information in this. And here the lambda, here is the radar wavelength. However, there are several, this is oversimplified, there are several complications, and one of them is this modulus 2 pi. So in the end here, the phase we measure and record is just a fractionary phase. It's not the absolute phase. All these number of oscillations, we don't know them. We just measure a phase between plus and minus 180 degrees, or equivalently pi, plus and minus pi radians. That will turn out to be a bit of a complication. But some sensitivity to the distance is there. To understand things more thoroughly, we need to get a little more quantitative. So if we have a SAR flying and looking to the side, as you saw yesterday with Helmut, if you then download some imagery, some so-called focused SAR images, single-look complex products from the European Space Agency or other satellites, well, the position of objects, they are stored at the so-called Doppler coordinates. So a point on ground, like this corner reflector, will be stored at the azimuth time of closest approach, this one here, where the satellite is at the closest distance from the point on ground, and at the slant range of closest approach, this distance R0. So the two radar coordinates, slant range, so distance from the satellite, and flight path direction, azimuth, they are the zero Doppler coordinates, and regardless how this physical antenna was pointing, you have always an azimuth time and a slant range of closest approach. That is where an object will be recorded in a focused radar image, a so-called SLC product. So, a point target, like a corner reflector, does not appear as a point in a SAR image. It light brightens up several pixels, and this is reflected by the fact that here its amplitude has actually a profile which looks here mathematically a bit like a sine x over x, sine pi x over x function. We don't care too much about that. It's centered here on the zero Doppler coordinates. We also have the phase term we discussed before. So when I focus our image, we have a phase term which is proportional to the slant range, so the distance of closest approach, and the radar wavelength appears here as well. We also have another term which depends actually on the so-called squint, so on the physical pointing of the antenna. In this course, we're going to neglect this term, although it can also be exploited to measure motion. So the interesting part comes here. If we now consider two satellite images, and there has been a change in either direction, so either in the slant range by an amount delta r, or in the azimuth position by a delta eta here, then we will have some sensitivity to these changes, both in the amplitude terms. Our point target is now in a different position. Our feature of the glacier is now in a different position, amplitude, but also in the phase. So the phase term, the slant range has changed, and so has the phase term. Indeed, this sensitivity will be exploited by amplitude-based techniques such as offset tracking, and this phase sensitivity will be exploited by phase-based techniques like interferometry. And here maybe you can already guess some different properties of these measurement techniques. So for example, if you look at the amplitude-based techniques, as you know, in general, motion of glaciers is three-dimensional. In how many dimensions will we be able to measure motion in an amplitude-based technique? What do you think? Any guesses? Two. Which dimensions? The two dimensions of the image, like we saw before in the glacier. It moves like this in the two dimensions, slant range and azimuth. What about the phase-based technique? In how many dimensions will we be able to measure motion? Only one. Which one? Slant range, because indeed here we have no sensitivity to azimuth motion. We would have in this phase term, but that actually is more complicated to exploit because the sensitivity is very low. Here instead it is very high. So if we look at, let's say, to give you an order of magnitude here of an overview of the sensitivities and some other properties of these measurement techniques. So if we look at large displacements, indeed, with two images, we can measure motion in 1 or 2 dimensions, and the achievable resolutions, they will depend on the imaging modes of the satellites, which generally trade off coverage for resolution. So the wider the coverage, the coarser the resolution, the smaller the coverage, the higher the resolution. And also the accuracies are different. So they are in order of magnitude more for the phase-based methods compared to the amplitude-based methods. Can any of you guess why? What image properties influence the sensitivity of amplitude-based methods? compared to phase-based methods? Why would we be more sensitive in a phase-based method? So if we want to achieve high accuracy with amplitude-based methods, tracking features, what system property do we rely on? What? Spatial resolution. And spatial resolutions, they are in the order of meters for Sentinel-1, 5 times 20 meters. Yeah, you can get in the order of even 10 centimeters, even 5 centimeters for these ISI images, which are this small. But that will not help you so much to monitor the glaciers of Greenland and Antarctica, too small. What about phase-based techniques? What radar parameter influences their sensitivity? If you look at this equation here. Anyone? Wavelength. And the wavelength is that meters? Microwaves? Centimeters. So we have a sensitivity which is of a different order of magnitude, and that basically means that we can achieve accuracies which are some fraction of the spatial resolution with amplitude-based techniques, and accuracies which are some fraction of the centimetric wavelength with interferometric techniques. Of course, we can use also more than 2 images and increase our sensitivity, but for snow and ice covered surfaces, this is problematic for reasons we will understand in the course of this lecture. Okay, so let's start with the first technique, differential SAR interferometry, and, which is a phase-based technique. And I'm going to give you a top-down introduction in the sense that first I'm going to show you some results of interferometry, and we'll try to understand progressively what is it we are seeing. So we start with a cliff in Greenland, here in the west of Greenland, Karafjord, where there was a big landslide in 2017. And many researchers like me working with interferometry, we were trying to measure the motion associated with this landslide. So I'll start by showing you this, which is a so-called interferogram of this cliff. An interferogram is the basic thing we observe in SAR interferometry, and it is a map of phase differences. As you see here, it's between minus pi and pi radians, minus 100 and 180 degrees, so on the unit circle. It is a map of phase differences in time and in space. In time, because it is between 2 images. In this case, likewise, between 12 days apart, between 23rd of October and 4th of November 2014. But also in space. As you see, these different colors means there is a phase gradient, a phase variation throughout this image. However, not all interferograms on this cliff look the same. This is an interferogram formed, so a phase difference map between images 6 days apart on the same cliff. And as you see, it looks pretty different. So something is influencing these phase changes a lot. So one could say, well, this is 6 days, this is 12 days. Maybe all 6 days look like this. How about this? It's also 6 days, and it's very different from this one. So you might have some legitimate questions. What is influencing all these colors and making all these phase patterns change? If your eyesight is better than mine, also you have noted that there are some parameters scribbled up here. Bn minus 6 meters, Btemp 6 days that we mentioned. What are these parameters? And maybe they also have an influence. So again, we must go a bit more in depth to understand. So let's, interferometry is, an interferogram is a phase difference image. Let's look at single SAR images. This is the amplitude of that cliff in Greenland, and this is the phase. As you can see, the amplitude looks a bit like a black and white optical picture, a microwave picture. Instead, the phase looks pretty, how does it look? Messy, random, to say it more scientifically, but yes, messy. Then let's try 6 days later. No, still bad luck. Amplitude looks good, phase looks messy. But magically, if we look at the phase difference between those 2 images, well, this is how it looks here to the right. So mess minus mess gives something which is still messy somewhere, but not everywhere. And if we look to the left, we see that it's still noisy, the phase difference is still random in places where a parameter called interferometric coherence is close to 0. And instead it's more deterministic where this parameter, interferometric coherence, is close to 1. So what is going on here? we need to get a little more quantitative and understand what phase terms we have in a single focus SAR image. As we said before, we have a deterministic phase term, which is related to the propagation delay. We have, however, also a random term, which is due to what we call speckle. Speckle is that something you have seen with Helmut yesterday? He mentioned it, right? Yes. So it is due to the interference, coherent interference of elementary scatterers within the resolution cell. Resolution cell of several meters, the arrangement of scatterers at a centimeter length affects the final phase value we get from that resolution cell. And it will be random at different times, this disposition of elementary scatterers. This gives rise to a random term. The deterministic term contains indeed an information we are keen on, so this distance information, this R0, but unfortunately it also contains other delay information which is not related to distance, atmospheric propagation delay, because we are from a satellite at 600-800 kilometers, we traverse the whole atmosphere. What happens if we see two images? They both have, in general, acquired from a slightly different orbital position, so they have different R0s, different distances. They have experienced different atmospheres, for example, 6 days or 12 days apart. And in general, they have the elementary scatterers in the resolution cell have a different arrangement. So these random terms are also different. So if we form an interferogram, so we form this by a complex multiplication whose phase is the phase difference, this phase difference will have different terms. A deterministic term, which is the difference between R0, an atmospheric term, and we will see how that looks, which is the difference of the two atmospheric propagation delays, and a speckle term, a difference of two random quantities, random variables. In the deterministic term, the only term we are interested for motion measurements is the one due to changes of position on ground at different acquisitions. There are, however, also other contributions due to topography and simply to the horizontal position of the scatterers on the Earth ellipsoid. And then we have atmospheric and the so-called decorrelation phase, which is this phase difference between speckle terms. As we saw before, the phase we record, so if we have two complex images, single look complex, their phase is between minus pi and pi, and their phase difference when we form an interferogram is again a number between minus pi and pi. This cannot be proportional to distance. We see it so-called in a wrapped version. So we see a phase between minus pi and pi. We would like a phase which is proportional to changes in distance, changes in R0 due to motion. There will be a complication there. So let's try and understand what we see. So in this area here, which is actually a fjord in Greenland, which phase difference is predominating of these ones? Which contribution to the phase difference? The noise one. The speckle term is dominating. Here there is well, I dare say a glacier. I'm an engineer, so careful when I say things about glaciers. I think this is a glacier, so which term is predominating of these? Sorry? The slope? Well, hopefully if the glacier is moving, there is some motion contribution here to this term. What about the atmospheric term? Could there be, is there any atmospheric term in this interferogram? In this, what do you say? What do you guess? Because we don't know. No atmosphere? Yes, atmosphere? Well, the other phase variations we see, it's either something moving, and moving quite a lot, or it is atmosphere. We will have to figure that out. But anyway, as you see, there are other deterministic contributions. Let's have a look at this R01 minus R02. What causes differences in that? We said it's not just motion. So there are these two terms, the so-called flattening and the so-called topographic phase, which cause changes to this deterministic term. So if I have this blue pixel on the Earth ellipsoid and a yellow pixel on another point on the Earth ellipsoid, As you see here, so this blue triangle, this distance difference, R01 minus R02, is this thick blue line. For the yellow point, this R01 minus R02 is the yellow line. So there is a change in this deterministic term. And that is actually what we see here. So if we have a flat area, and we look at this interferogram of this flat area and how the phase changes across this flat area, we see these dense fringes, so these dense changes in phase difference. They are due to the so-called flat Earth contribution. So this change between the blue thick line and the yellow thick line. They are these stripes we see here. Also, topography has a change. So if you look at here, we have a mountain ridge. We are someplace in Africa. And here you have some perturbation of this regular stripy pattern, as if someone punched through a regularly stripy pattern. This is sensitivity to topography. And if you look at the yellow dot compared to the black dot, they are at the same horizontal position, so same latitude and longitude on the ellipsoid, but different height. Again, the interferometric triangle yields a different difference. R01 minus R02 is different between the thick yellow and the thick black. That will give a different contribution here in our interferogram. And that is why we see a perturbation in the interferogram. We have a sensitivity to height. This sensitivity to height is regulated by the normal component of what is called the interferometric baseline. The interferometric baseline is just a jargon to say the difference between position vectors of the two interferometers, of the two satellite antennas. And the normal component is normal to the so-called line of sight of the satellite, so this component. This regulates how much phase variations are influenced by changes in topographic height. If we have a close to zero perpendicular baseline, we are not sensitive to height variations. In practice, we will actually be forming some differential interferograms. So in fact, all the interferograms you have seen here in my previous slides, these ones, also these ones, these are all differential interferograms where we have actually removed these flattening and topographic phases by using an Earth ellipsoid model and a digital elevation model. So we can remove these terms, but still, if we have errors in our digital elevation model, for example, because we didn't update it, as Frank mentioned, then still we might have a sensitivity to these errors, but only if our perpendicular baseline is relatively high. So perpendicular baseline close to zero, we don't have sensitivity to height variations or to possible errors in our digital elevation model. What about sensitivity to motion? That's what we're interested in this lecture. Well, let's consider the case where we have a zero baseline. So at the two acquisitions, the star was exactly in the same orbital position. In this case, these flattening and topographic phase are zero. Still, if there's a motion, for example, this exaggerated uplift, this orange arrow, meaning there's been some inflation, strange kind of inflation here, we will measure a change in R01 minus R02, which is due to the projection of this three-dimensional motion vector onto the radar line of sight. And this projection will be proportional to a phase variation through this 4 pi over lambda, where lambda is the radar wavelength. So this also means that what line of sight or range deformation do I need to cause a full cycle, so 2 pi radians deformation? How much change in this R01 minus R02 do I need to get 2 pi on the other side? Any guesses? Something to do with the wavelength.
2 times the wavelength.
So if I put 2 times lambda, I will get 8 pi here. How much do I need to get 2 pi? Half wavelength. So if I have half a wavelength for Sentinel-1, 2.8 centimeters change of so in motion in the range direction, that will cause a phase fringe. Here, from color to color, there is a phase fringe, a 2 pi radians. So if I see a phase variation of 2 pi, if this is due to motion, that is lambda halves of motion. If we have a glacier, for example, moving at a steady rate, an interesting thing is that this slant range motion will be due to a constant velocity in the slant range direction times the time of observation between the two images. So now some questions for you to see if we can explain a bit more of what we see. We have this 12-day interferogram to the left, the 6-day interferogram to the right, and I'm pointing at an area where we have probably some moving ice. I don't know if it's a glacier, but some moving ice. Why do you think we see more fringes here to the left than to the right? Any ideas? More time between the two. So we have roughly, well, we have the double time between the two. So if things are moving at a steady rate, so the velocity projected onto the slant range is the same, if it's a steady rate, the time is times 2, so the phase variations are times 2. Okay, if it's moving at a steady rate. Make sense? Are there any questions? Let's have a look at something different. Let's have a look at these other interferograms. Same area. As I told you in the beginning, I was studying this area for landslides, not for glacier motion, because indeed here there are some areas of the slope which are sliding. Could you tell me which ones you think are sliding? We have 6-day, 12, 18, 24-day interferograms here of the same area. And as you see, there are many phase differences between these images. Where is there some moving areas, and why do you think it's moving? Middle to the left?
Yeah, down towards the one.
Yeah. Why do you think this area is moving?
You see fringes in the 6 days,
Yeah.
one, and then the 24 days, it's quite big.
Yeah. So first you see a bit more fringes from 6 to 12 days to 18 days, and then, indeed, some areas start to decorrelate, and that is also something related to the motion, or we will see some sources of decorrelation. The phase differences start to become noisy. Are there other areas which might be moving? What about this here, for example? This is all red here. It's not red anymore. What is going on here? Is that motion? Would it be consistent with this discussion if there's some steady motion? Are these fringe patterns consistent with that? Up here, for example, where it's all red here, it's bright red, then here it's not, here's blue, red again. Is that consistent with motion? Not consistent with motion. So we'll have to find another explanation. It's not consistent with what we're talking about here. Indeed, actually, the main landslide area was this area here, and there are some areas which are still decorrelated because there's a lot going on there. There's like a constant flow of debris on those areas. So they are decorrelated in all interferograms. So we cannot measure motion in this period of time here. But indeed here there was an area which nobody knew was moving before it was mapped with interferometry, and which here clearly we see is moving. Okay, let's have a look at this interferometric coherence which we have mentioned. So we have said that where this parameter is close to 1, we can carry out interferometry, where it's closer to 0, we cannot. Interferometric coherence is just a measure of similarity, statistical similarity between the complex values of the two images. Close to 0, so 0 means complete decorrelation, images are dissimilar. Close to 1, 1 means identical, they are totally correlated. Statistically, this phase difference between the speckle contributions is narrow when coherence is high and approaches a uniform distribution when coherence is 0. So basically, in doing an interferogram, the random contributions will kill each other, cancel out when images are statistically similar, random but similar, and will not cancel out. And so the whole thing will still look random when the images are not coherent. They're not statistically similar. Those random terms do not cancel out when we do the phase difference map. There are many things which can contribute to the correlation. So the spreading of scatterers, both horizontally, that's geometric decorrelation, and vertically, it's volume decorrelation, for example, due to penetration in snow and ice. Then there is temporal decorrelation, so if there are changes in the surface properties, or even just in the electromagnetic properties of the surface at the time of the two acquisitions, this will cause decorrelation. And then there are things which are less interesting for us, these thermal noise and processing decorrelation terms. So spreading of the scatterers, horizontally or vertically, and changes in time of the surface are the main sources of decorrelation which we usually have to deal with. And now a question for you. Here we have two situations. We have the cliff we've been watching until now, a coherence map, an interferogram. I give you also another area here. This is an urban area, Kumamoto, Japan, urban area, some forest, coherence map, and a lot of phase changes due to a very large earthquake between the two images. Can you mention, so any sources of decorrelation? For example, where is it that we have so-called temporal decorrelation? So loss of coherence because of changes in time of our surface. For example, let's start from here from the Greenland example. Where do we have temporal decorrelation? Here we have black, black. Where do we have temporal decorrelation? This is a cliff and this is a fjord. Where do we have temporal decorrelation? The water. So a patch of Greenlandic fjord, 6 or 12 days apart, will look statistically different in a radar image. Zero correlation, temporal decorrelation. What about here in the Kumamoto case? Why do we lose coherence here in this area compared to the urban area? What is causing decorrelation here, if you look at the optical image? The vegetation. In the vegetation, if you think of these sources of decorrelation, distribution of the scatterers in different dimensions or changes in time, which sources of decorrelation could? Volume, because we might have penetration in the vegetation, depending also on the radar wavelengths, and possibly also temporal. Vegetation tends to, some vegetation tends to change in time, and that can lead to decorrelation. Okay, then there are, as you see here, there's also a correlation with some ice or snow-covered regions, also decorrelation. You can imagine a snowfall between the two images. That would be which source of decorrelation? Sorry? Volume, well, of course there could also be some volume decorrelation, yes, but certainly it would change the surface properties between the two images. So probably a mix of temporal, I would guess the dominant one, and maybe also volume. Okay, but we have still one unexplained fringe pattern here, right? This is not decorrelated, it's deterministic. So I have two things here. Either this is motion, and if this is motion, how much motion do I have between the base of the cliff here, the foot of the cliff, and the top of the cliff here? From blue to blue, that's a 2 pi phase difference. So how much motion would I have if I should interpret this as motion? Sorry? You can count it. I can count it. This is one fringe, so it's an easy count. One fringe is how much motion in the range direction? Let's say towards and away from the radar, how much motion? Half, so 2.8 centimeters, half a wavelength, this is sentinel. So either the top of the cliff is moving 2.8 centimeters compared to the foot of the cliff, major earthquake, or something else. What can the something else be? Atmosphere. So when we don't know what it is, it's atmosphere in interferometry. Of course, in this case, I know there has not been an earthquake, so it's atmosphere. And indeed, without going into details, we traverse the troposphere, the ionosphere, and there is a propagation delay. And some propagation delay are tricky, because some are due to variations in water vapor, and they appear a bit random, and they are easier to distinguish from motion, which is typically spatially correlated. But others are due to the changes in the vertical stratification of atmosphere, and they are very correlated with height. And this is what we see here. The atmospheric variations are correlated with the topography of this cliff. One would almost think, I used the wrong den. No, This is just changes in the vertical stratification of the atmosphere at those two epochs. So far, so good. So we can use interferometry as long as the interferometric coherence is sufficiently high for the deterministic terms to prevail in our interferograms. And only some contributions in our interferograms are sensitive to motion. Motion, however, in the radar line of sight, so towards or away from the radar. It's only one-dimensional motion we measure. However, to get from working principles to a processing chain, there are some things to keep in mind. We will see this more in detail when we go to the exercise. This is just to give you some background for that exercise. So we mentioned, this is our unknown, the deformation term. Flat Earth and topography, we can remove because we have ellipsoids, we have DEMS. Decorrelation, well, we cannot remove it, but because it's spatially uncorrelated, as you see, we can do some spatial averaging to reduce its effects. Atmosphere, a big problem. It's very tricky. If we just have one interferogram, it's very tricky to, we can be misinterpreted for deformation. Then we have this modulus 2 pi, and we have only seen phase variations between minus pi and pi until now, but to recover motion, we will have to unwrap these phase differences and carry out an image processing step called phase unwrapping in 2 dimensions. Very tricky step. So, high-level processing, our first goal is to get our best estimate of the wrapped interferometric phase, like the interferograms you have seen until now. And we'll also generate a map of coherence as a quality parameter, because we know that where coherence is 0, our phase differences are unreliable, not related to motion. Part 2, we'll have to unwrap these phase differences we have seen until now and scale them so that they will be measurement of motion towards and away from the radar. Let's have a look. To make a map of phase differences, actually, our first prerequisite is that the images are aligned, or as we say in SAR jargon, co-registered. So the pixel in image 1 must be at the same position in image 2 if I must make a per pixel difference, phase difference of these images. So first I align the image, and then, only then, I am ready to form the complex interferogram like this by a complex multiplication, and its phase term will be proportional to the difference, phase difference between the two images. So co-registration. So in general, for sentinel images, we have the two images, we'll have to co-register, then we can form a so-called differential interferogram, meaning that the phase difference will look stripy. Then we take away some known terms, and these need in general to be filtered a bit because the phase tends to be a bit noisy. I'll show you an example which has nothing to do with glacier motion. It has to do with an earthquake because these techniques are applicable also for those. Just to show you these processing steps. So here we have a phase difference spanning a large earthquake in the area I showed you before. And this is what the phase interferogram looks. We can see all these phase variations. They are due to motion and to a fault crossing this image like this. It's very noisy. This is what happens after I perform a filtering technique called multi-looking. This is what happens after I perform an adaptive filtering called a Goldstein filtering. So we went for a very noisy phase difference, estimate of interferometric phase, to a clearer phase difference. Multi-looking is just at a high level. It is just making a complex averaging in a box, taking away first the flattening and topographic terms, and then taking the phase of the averaged complex number. So a very simple averaging. This Goldstein filtering is more complicated. Basically what it does is a bit what your eye does. If I look at this area, I can see there are some underlying fringes buried in noise. My eye enhances those fringes and makes me see them. The computer is even better at that. So here it gets rid of the noise and enhances, gives a boost to the dominant fringe patterns locally. We don't go into the details of this. You can read the reference papers if you are interested in. So once we have this, and here is our coherence map of the area, higher in urban area and lower in vegetated areas. Coherence estimation is a little tricky because in its definition there is an expected value, and we cannot observe expected value. I would need to have different realizations of the same resolution cell, which I don't have. So these expected values are in practice replaced by spatial averaging, assuming that neighboring resolution cells are different realizations of a same stochastic process. So once we have our best estimate of interferometric phase and coherence, we need to unwrap. That means that, as a colleague said before, we count the fringes. Here I count 5 fringes, blue to blue to blue to blue to blue to blue, and so on. If I unwrap it, that means that I see a linear phase gradient in this case. We can only unwrap phase differences under the assumption that variations between neighboring pixels are not greater than pi in magnitude. Otherwise, we have an ambiguity in our unwrapping. In areas where the correlation prevails, so these random terms prevail, this assumption is not met because we can have big fluctuations in phase, and our assumption is not met. So most unwrapping algorithms will give up and not give you a result. So we cannot always count on having a result from unwrapping. But as you see here, elsewhere, indeed, we have succeeded in unwrapping the phase differences between pixels. However, unwrapping is spatially relative. So conceptually, we always have a starting point, a spatial reference. So we don't have the absolute phase, as we mentioned in the start. We recover the spatial gradients with respect to one point in our image, in this case, this star. At this point, we can finally scale the unwrapped phase, multiplying it here by lambda over 4 pi, and get the line of sight motion, with one thing we must keep in mind, which is the sign. The sign of our line of sight deformation, well, we just measure motion towards or away from the radar. Should towards the radar be a positive motion or a negative one? It is completely up to you when you process the image. There is no convention for this. So whoever gives you a line of sight motion map must tell you what convention they chose. I choose a minus sign, which corresponds to having positive motion towards the radar and negative away. But this is just my choice. We will see this in the exercise. So this is the end of an interferometric processing. We have seen it in radar coordinates. Usually we want to geocode it, so basically resample it to a map projection. And this is still motion away and towards the radar. The only catch is that sometimes it's tricky to remember that interferometry only measures one-dimensional motion, and the original motion is three-dimensional. So for example, in this case, we have an earthquake fault oriented like this, and this part of the fault moves up, so north-east, and the bottom part moves down. So it's moving like this. And we have a satellite flying in this direction, ascending path. So why do we measure motion away from the radar in this part? We have a motion like this. The satellite is flying here. Does it make sense that we measure motion away? Yes? Well, we have a eastward motion here. That's what the red means. So eastward is that way. The satellite is flying like this, looking to the right, in this case. So motion is away from the radar. That's why we have this. There's also a downward motion, which also means motion away from the satellite. So there are two contributions which give this bright red. Here instead, we have a westward motion. Satellite is flying like this, motion like this. Satellite looks right, so motion towards the radar. So we must remember, in general, interferometry, we measure the line of sight projection of three-dimensional motion. And this applies, of course, also to Glacier motion. Could this cause some problems in our motion measurements? Could there be some situations where we cannot measure motion? For example, if you consider the orientation of the glacier, could there be some orientations which would be very unfavorable to measure motion? So if we are parallel to the flight path, then with differential SAR interferometry, we won't measure motion. Okay? But, of course, we have ascending and descending passes. So what we don't see in one geometry, usually we see in the other geometry. So that is something which we must keep in mind. There are also techniques to measure motion in the flight path direction, and one of them is offset tracking. Are there any questions before we jump to offset tracking? Yes? Coherence is estimated on a, let's say, not per pixel basis, but on an estimation window. We will do that in the exercise. Sorry, once again? Yeah. Well, if I chose my reference in a moving area, then non-moving areas would suddenly move, right? Because we are just measuring gradients with respect to a reference. So when we choose a reference, we must know something about what's happening in that reference, because all the motion is referred to that. That can be tricky. Other questions?
So can you use this for fast-flowing glaciers, or are they moving too fast?
Yeah. So indeed, if things move, interferometry likes gentle movements, because otherwise coherence is destroyed. Usually when there's a fast movement, Frank showed some videos. There was a lot of things going on, all cracked eyes moving. That's too violent for interferometry. Probably even for offset tracking. Too many changes on the surface. Coherence is destroyed, and probably also the features in that case. So there we just need the time lapse Frank showed you. Other questions? No? Then we hop on to offset tracking, which is an amplitude-based technique, and employs these amplitude terms. And so this answers directly your colleague's question. But aren't we already happy with interferometry? Well, we discussed now a limitation of that. If there is fast motion, well, we can't keep up with it. And also, if we have motion in the flight path, we can't do much with interferometry alone. So here is a Rink Isbre data we will work on in the exercise. So again, Glacier flowing down here. And 46 days data in a Japanese L-band image. Let's use interferometry. Look, we are flying here. We are looking straight into the glacier. Shouldn't we use interferometry? This is the coherence. Can we use interferometry? Dark blue is 0. Can we use interferometry? No. Example of why we cannot always use interferometry. However, we can hope to use offset tracking. So this is a microwave image of a glacier. It resembles an optical one in the sense that there are some crevasses and other features on the glacier, which we see also here. However, this is an optical image of the interior of an ice sheet. I don't know if it's Greenland or Antarctica. It doesn't matter. It's all white anyway. This is the radar image of the same area. Is it featureless? Here there is a random speckle pattern. And as we said before, speckle is random. But if there's a statistical similarity between speckle patterns, we can still track that. And that we cannot do with optical imagery. If there are no features, then there's nothing to try to measure motion with. So indeed, speckle, as you see on this glacier, if I despeckle it, this is how it looks. Speckle gives this salt and pepper, black and white salt and pepper amplitude fluctuations on the glacier and on other parts. And it is a nuisance if we are after features, looking for features, or maybe for Frank's glacier delineations if you were to use radar, but it can be a blessing to carry out motion either on featureless areas, such as the interior of the Greenland ice sheet in this case. When we say track features, conceptually what we want to do is take a patch of data in one image and search for that patch of data in a search window in another image. So we call the patch of data a template window, and we call the area we search in a search window in the other image. And the way we carry out this search, there can be different ways. Mathematically, there can be different ways. I will show you a way which is called normalized cross-correlation. So a two-dimensional cross-correlation, which also does some normalizations to be less sensitive to amplitude changes. So when we have a normalized cross-correlation of +1, it means that we found a match, strongly correlated. When it's -1, it is strongly anti-correlated, not good. So conceptually, we take a template in image 1 and search for it in the search window, when we have a match, we will get a peak in this normalized correlation. And in general, we will have a 2D cross-correlation surface which looks like this. The position of the peak compared to the case where there is no motion allows us to measure the two-dimensional motion of a given point. And the peak can be due to features which we are tracking, like we saw in the very beginning, or to coherent speckle patterns, which also can give a cross-correlation peak. This cross-correlation peak not always looks very peaky. So this is good case, good case. This is a mess, because here there's a peak, but there's a whole band of cross-correlation. So as a quality measurement, one of the many which is being proposed is a so-called signal-to-noise ratio of this cross-correlation strength, which is basically a ratio between the peak cross-correlation and the average cross-correlation of the background. It is one quality measure which we will also use in the exercise. So to form a map using offset tracking, we have to repeat this process. So we position a template window, search for it, analyze the position of the peak. We have a two-dimensional measurement. Then we place another template window at some distance from the previous one and repeat the operation. This measurement spacing is up to us. The tighter, the better, but also the more calculations. As we will see, it takes a lot of time to do these calculations. So measurement spacing is our choice. In general, we can also co-register these images. That will simplify our life. We will have to deal with outliers, and then we'll have to convert these offsets to motion. No unwrapping is required, because once we measure the two-dimensional offset, that is not ambiguous. That is directly convertible to motion. That's also a great advantage of offset tracking. It's two-dimensional and doesn't require unwrapping. We should also dimension the template window and the search window properly, because the template window must be large enough for what? What do you think? If I have too small a template window, what problem might I run into? Lose the feature. The template must be big enough to include enough features, for example, or enough speckle. What about the search window? What will that depend on? For the patch of data, where must I look for it? If I have some idea of how fast this glacier cannot move infinitely fast, so I look only within a certain area. So search window must be dimensioned according to that, template window according to the features. And these choices will also influence the resolution of our measurements. So it's a bit tricky, because if I do feature tracking, I could be lucky, and I place a window here, I track a feature. Next, I move it, there is another prominent feature, and I track it. I have two independent features which I've tracked. But I could be unlucky. I could get stuck on a feature. So I have a template window. There's a dominant feature I track. I keep moving it, and it's still that dominant feature which is giving me the cross-correlation peak. And I can be stuck for a whole template window size measuring the motion of the same feature. So the resolution is somewhere between the measurement spacing in the best case and the template window size in the worst case. It is very difficult to have some error characterization. Of course, the stronger the feature, the better. Of course, the larger the coherence, the better if we're tracking speckle. But these are bookish expressions, because we do not know at a given point if we're tracking a feature or speckle, and we do not know exactly what feature we're tracking if we're tracking a feature. So these error estimates can only give you an order of magnitude for the accuracy of these measures, which I've given you before. So in the order of, 10 centimeters on a pair of Sentinel-1 images. But error characterization in practice is done in a much more empirical way, because we don't know in practice what we are tracking.
No, but I don't understand how it can be 10 centimeters if the spatial resolution of...
Yeah, well, yeah, because we achieve some spatial resolutions which are even 100, in the best case, even 100th of the spatial resolutions. So our accuracies are between 1/10 and 100th of the spatial resolutions. This is because even though we have these spatial resolutions, well, actually our data is, let's say, sampled well enough to represent the underlying variations. We have more information in our images than just, we have samples of an image. We have more information actually than the samples we have. We could reconstruct a continuous image if we interpolated, let's say. So we can see some sub-pixel details in general.
But when you're looking at the same picture on the same spot,
Yep.
if we pass it to the you convert it to displacement pattern, then you can see there's different orientations, so you can filter a little bit with that same picture.
Yeah, that can reduce the noise, definitely, yeah. Other questions? I have just one here, final slide, which is, in practice, interferometry offset tracking, they are not two techniques which either use one or the other. They are complementary. This is an area here in northeastern Greenland, a mosaic based on offset tracking alone. Resolution 250 meters. We need a certain template window size, but very good coverage of the fast-moving regions. Some noisy things here, due to ionosphere actually. Interferometry. Much smoother here on the interior. Here, it's Armageddon of phase unwrapping errors here. It's a disaster. This is unreliable, to be thrown away. Merger of the two, good coverage of outlet, and high resolution and less noise in the interior. So, in general, we use all the techniques we can apply with the pros and cons they have. Any final questions? No? We look forward to a coffee break. So, thanks for your attention.